Okay, I want to welcome the people who are here and the people who have tuned in from Zoom. We are having potentially some camera issues. If you're not seeing the room on Zoom, you should be seeing the PowerPoint. If we don't get that working, you will still be able to ask questions and interact. We apologize if you're not getting a camera feed. It was working 30 minutes ago and suddenly it decided not to. But anyway, I want to welcome you to our first hybrid lecture of the 2022-23 school year. And today we welcome Dr. Norman Tennent, who is a longtime friend of EODIA. I'm Michael Thomas, the director of the Edith O'Donnell Institute of Art History. And as I said, I want to welcome you to this lecture. I'm going to ask two things first of our people who are attending via Zoom. First of all, would you please go ahead now and turn off your mics, and you'll get a chance to turn those back on later. But actually, the best thing, then after the lecture, we are going to have questions both from our audience here in attendance and from you on Zoom. We ask that those of you on Zoom, please utilize the raise the hand feature that's on Zoom when it comes time to answer questions. And then finally, if you're experiencing some technical difficulties, please do not hesitate to put any questions or issues in the chat. And Katrina Saunders, who's here monitoring that. Okay, great. So as I said, we're welcoming today Norman Tennent, Emeritus Professor at the University of Amsterdam since 2014. He graduated with a PhD in chemistry from Glasgow University and worked as a postdoctoral researcher at the Ohio State University. In 1975, he was appointed to establish a new conservation science section for the Glasgow Museum of Art and Art Galleries, where he remained until 1987, when he began a career as a freelance conservation science researcher, teacher, and consultant. Research interests include polymer degradation and stability, indoor atmospheric pollution, the technical study and conservation of inorganic materials, and the reevaluation of former conservation treatments. He is a former editor of Studies in Conservation, founding editor of Reviews in Conservation, and has more than 100 published articles. In 2001, he was appointed to a special chair at the University of Amsterdam and became the first full professor of conservation science in 2009. We are lucky because since 2016, Norman has been associated with the conservation science at the Edith O'Donnell Institute of Art History and was appointing visiting conservation scientist at EODIA in 2018. So I welcome Norman Tennent, who's going to present Slow But Sure, a good motto for heritage science.
Thank you very much indeed, Michael. And indeed, it's a pleasure to be back in Dallas, back at EODIA, and to be meeting new colleagues and some old ones after 2 disruptive years, shall we call it, for everybody. My talk today, and I hope those in Zoom are going to be able to receive it loud and clear as well, is entitled Slow But Sure, a good motto for heritage science. And maybe I should say why heritage science and not conservation science. And that's basically because heritage science is the broader term that's used these days to encompass certainly conservation science, but also what's known as archaeometry or technical art history, the investigation by analysis of compositions and the like. So that would cover heritage science. Slow but sure. Well, why slow but sure? For this talk, it's because it's very much an important factor of the slow process of the degradation of art. The degradation of processes of all sorts of art, and we'll see examples in this lecture. And it's also relevant to the slow, or should we maybe better say long-term experiments that need to be done by those involved with conservation to determine how materials and processes for conservation are going to stand the test of time. I'll begin with some more general examples rather than conservation or heritage science of what is slow, painstaking research. And thereafter, I'll begin to develop some of the various themes, miscellaneous themes that I've been involved with myself that require slow processes or slow and long periods of research. There'll not be too much hard science. An equation has slipped in by default, and I think a spectrum or two, but basically this is a descriptive talk, and I hope you enjoy it. I think this should bring up, indeed, the very first example of slow but sure research. Do you recognize them? My knuckles. But in fact, it's not my knuckles that are important, but a young doctor who was a youth decided that his grandmother may be right or may be wrong when she told him, if you crack your knuckles, you'll get arthritis. So he started an experiment. For many years, he cracked the knuckles of one hand only. And then after a suitable amount of time, it's estimated that he had cracked his knuckles 35,000 times. He decided to check if one hand had arthritis and one hand had not. And of course, found both were perfectly good, lucky man. And indeed, that many decade experiment was valuable and validated subsequently by a study of patients who also revealed that there is no relationship at all between cracking your knuckles and getting arthritis. Well, that's very lighthearted, but actually it's not so distant from the kind of things that go on in conservation science. And certainly to be able to have the patience and the determination to keep going over years. This is relevant in a general way to the moment of the lecture, because in 2 days from now, an exhibition will open at the British Museum, which will feature the Rosetta Stone. Well known to everybody, well known for all sorts of reasons, for the intrigue of how it ended up in the British Museum, for one thing, and for especially the translation of the hieroglyphs that are engraved upon it. Discovered, of course, in 1799, but only came to the British Museum in 1802. And indeed, it was some years later that the translation process began to gather a bit of steam. And that's because of someone who is relevant later in this lecture as well. A polymath, a medical man, scientist, the person who developed the wave theory of light, which complemented Newton's particulate theory, both of which still are necessary to explain light these days. And that's why we'll see him later. But he began in the early 1800s to apply his general intellect to the translation. And indeed, it was thanks to his initial investigations that the Frenchman was recognized as being primarily responsible, and whose 200 years celebration is being recognized by the British Museum for their exhibition, that developed the whole translation of the hieroglyphs, based, of course, on the Greek and the Demotic Egyptian scripts that are virtually identical. So there's Thompson. And there's the slow process, because of course it was only in the middle of the century that the full English translation first appeared. Slow but sure application of science. I appreciated that too in a general way, because of course my alma mater is University of Glasgow, and here you see it in the left slide, in its building where it was moved from the centre of the city of Glasgow to the West End, in the 19th century, and where Lord Kelvin was perhaps one of the best known scientists that was involved with that university. We know him, of course, for the name that he gave to the degree of Kelvin, the temperature scale, But what is not so well known is that he lectured here and set up what I, as a proud Glaswegian, will claim to be the longest running experiment in the world. Correct me if I'm wrong. And here it is. He set up on the ground floor of the building that you saw on the left, 2 tubes, 17.5 feet long. Into both of them, he placed colored liquids, copper sulfate, the blue, and a red solution of alcohol. Top them up very gently with water and set that going. No more activity from the moment he set it up to the present day, over 150 years ago. Diffusion of the colored liquid with pure water is still taking place. Kelvin's not around to do any measurements these days, but the experiment exists. And the right-hand photograph is my shot of the close-up, where his writing is actually commenting upon the 2 liquids at that particular height in the building. It goes through 2 floors, from the ground floor, right up through the ceiling and through to the next floor. So, slow but sure, and possibly lasting beyond a single lifetime. This was perhaps, and it's the last general slide, but it's a conservation one, the inspiration for my being here at all. Because as a 16-year-old schoolboy, I was here in Stockholm to see the early days of the warship, the Vasa, which had been brought up from the sea, waterlogged completely, and had to be solidified so that the wood of the ship's hull did not distort and break up as it dried out. So even in those early days when I was 16, and that's not just yesterday, there was the process of spraying continuously with PEG. It's commonly known polyethylene glycol. It's a polymer that can diffusion again, into the waterlogged wood. And for 16 years, it continued to be sprayed. The result, of course, is now that this grand warship is in all its present glory. Thank goodness for conservation, and thank goodness for slow but sure. But unfortunately, conservation has to reckon with chemical processes that continue. And now there are problems emerging because of the acidity of the wood, and perhaps because of the breakdown of the polyethylene glycol, releasing formic acid. We'll see that again in a moment too. But the whole situation of the stability of this hull is now in doubt. But undoubtedly, it would not have been preserved had it not been for the slow but sure impregnation, documented in the PhD thesis, which I had the pleasure of being the opponent, as one is called, at the University of Göteborg, for the person who spent her whole life, also slow but sure, working on the conservation of the Vasa and the impregnation of the woodwork. Here she is, and her PhD was defended successfully, despite my interrogation, at the age of 75. That's perseverance for you. But what about conservation projects? Well, let's look at some of those that have demonstrated this in various ways. Problems that sometimes require a long time before they are elucidated, of materials that need a long time before they are justified as acceptable, and so on. Initially, let's look at indoor gaseous pollution. Well, of course, we can't see it. And indeed, I could have been presenting problems of silver protection from tarnishing, which was a project where we indeed tried to solve a rather long-term problem and stop it happening. Well, we got a certain amount of the way there, but that hasn't happened yet. But this is to do with a special kind of indoor pollution. And it's demonstrated by this slide, which is a simple shell specimen from a museum And the caption below the specimen card tells you the name of the process that's going on here. It's called Bine's disease. And Bine's disease was coined, the name was coined by Mr. Bine, surprise, surprise. But when? The end of the 19th century. And it still holds that name. We don't think of it as a disease now because he said that one shell would catch it and spread it to the next by a process he wasn't willing to elucidate. But indeed, that is true, that it seems to be so. Because here in the nickel collection of shells in the Royal Museum of Edinburgh, those scientists among us may know nickel from his nickel prism, same man. But he had a collection of shells, which on the right-hand side you see is in a drawer, which is not made of the fine mahogany wood of the cabinet, but is made of a wood. And there are several that are problematic. Softwoods and oak being primary amongst them, which evolve the relevant kind of indoor pollution that will attack what is inside. Well, in this case, it's very common because every museum collection of mollusks from that period has this as an ongoing problem to a greater or lesser extent. But from Bine's naming of the disease to the understanding of it, or even the beginning of the investigation of it, till the late 1970s, early 1980s, when a colleague and I began to really assess what is going on. And it became clear that it is part of this process of this type of indoor pollution that is being evolved from the wooden materials of the cabinets themselves, attacking, in this case, the calcium carbonate, the calcareous shell surface, and forming new compounds in some cases. In some cases, standard compounds that are well known to scientists and others. But in this case, we were finding that indeed it's not surprising perhaps that Bine could not identify exactly what was going on the surface, because these were compounds that only form, as far as we are aware, in special cases like this. They do not exist anywhere else in the world except in museum cabinets on objects. It's museum cabinet chemistry. And in this case, it's easy to see that some shells indeed are badly attacked, and some cases impervious. It's not spreading from one to another, but it's dependent on the characteristics, which we don't need to go into just now, but perhaps briefly seem to be connected with how well they had been cleaned in the first place. So some are affected and some are not, and they're affected in different cabinets to different extents, depending on the severity of the problem in those cabinets. And the type of material, here's the graph, is easily identified by infrared spectroscopy, for example, or other scientific techniques. But indeed, these are two infrared spectra. And all you need to know is not what the technique involves, but that it gives a picture of the atoms in the molecule and how they interact with each other. And the trace in each case, in one case above and one case below, one is of the actual sample from the shell. The other case is a sample that has been synthetically made in the lab to try and replicate this material that had not previously been known. And they do, they match. And other techniques can confirm that this indeed is a compound that is only known in such circumstances. Not a very complex or sophisticated compound, a calcium acetate formate. And the formate is related to the formic acid. And as you remember, formic acid is one of the problems that's now cropping up in the Vasa wood degradation product in its own right. So there's relevance there as well. But this is only one example of that kind of really mysterious and rather surprising indoor pollution affecting the objects within cases. And we don't need to go to world-class museums or smaller museums. We can go also to various places that might have works of art, or even just objets d'art and trinkets in cabinets. Because here at Beatrix Potter's house, the famous Peter Rabbit authoress in the Lake District in England, she had such a cabinet with all sorts of goodies that she liked inside. Not world-class art, but certainly objects that are being affected by the pollution inside. And of course, we can remember that shells are not just natural history specimens to be examined, but they're also transformed into decorative art, and sometimes rather valuable decorative art objects, which can also undergo such degradation. And indeed, not just shells, but the metals of copper-based objects. And again, these little objects, rather insignificant, from Beatrix Potter's house, not a world-class establishment, are showing new copper corrosion products not known in any other situation other than, well, not just Beatrix Potter's house, but some places where the acid pollution. Again, it's the formates and acetate type of compound from these acids that have been given off in some very small proportions, but enough over the years, slowly but surely, to cause the degradation we see. And then slowly but surely, since the 1980s, begin to be identified by researchers in various places. I was in the vanguard of that, but now the work has been taken up by many researchers who are still finding new chemical compounds as they look at various objects, glass objects, metal objects, and so on within cabinets. Slow but sure degradation and slow but sure development of the analysis. And of course, it's slow but sure from the scientific point of view, because actually it's only in some recent years that it's been possible to easily assess what is the nature of this compound. Techniques that were not available in the 1960s or 70s are now coming to the fore and able to sort this out. Raman spectroscopy being one of the most important. So we're better placed. The name here of this particular efflorescence product or salt growing on the surface of an object is its common name, efflorescence X. Common name until it was actually elucidated what it was. But, you know, when one's coming across new compounds here, there, and everywhere, efflorescence X is as good a name as any while one gets on with the identification. Well, the man that was helpful in leading to the identification of efflorescence X was this particular guy. He was the curator of the geological collections in Brussels, in the Natural History Museum. And he had already, before applying his mind to what this mysterious efflorescence X was, which has whiskery crystals growing out of objects, he'd already found this one. This was yet another new compound, only discovered in museum cabinets. It's a rich source of interesting chemistry. And he discovered calcrasite, which was from a calcium object, in this case, a rock specimen, reacting with, again, the acetic acid. Acetic acid is just vinegar to you and me. Small amounts from the wooden cabinets. And then the chloride is also there. So it's calcium, chloride, acetate, and that's the compound. And the chloride was present as salt in the residue in the fabric of the stone. And out comes, after a number of years, these crystals. In the process, consuming the original object. So this is a very degradative process. And if it happens to one rock specimen amongst hundreds, maybe that's not so important. But when it happens to a unique museum specimen that can also contain calcium, then this is more important. And so it is that when one goes to the British Museum, here is efflorescence X. in an Egyptian cuneiform tablet, causing the disintegration of the very friable pottery that has no great strength, and the growth of these crystals is beginning to push off layers of the tablet. And of course, if that has any kind of inscription, this is lethal to the usefulness of these objects in the museum. Well, again, it's another case where it was known that this compound exists. People could identify that it was the same compound here, there, or somewhere else, but they didn't know what. Science was not at that stage up to the task because techniques that would be useful to the elucidation were not yet available. And the one technique that was to be developed and then became applied was a technique called ion chromatography. And the only thing we need to know about ion chromatography is that when you dissolve up these salts, it can distinguish the various components. So it could find calcium, it could find chloride, it could find acetate or other components and how much they are, and therefore construct the formula for efflorescence X, which is exactly what we did. And here we have a slide coming up of the sample that helped us on the way, because there was any amount of efflorescence X pushing off the glaze. These salts are so soft that you could just powder them it in your fingers. But when they actually start growing, slowly but surely, in exerting pressure of the growth of the crystalline structure, it can destroy the hard glaze of a Dutch tile such as this. But the specimen that was most abundant in efflorescence X, and therefore oodles of sample to analyze, which scientists just love, was on an Egyptian carved relief, again in the Glasgow collection in this case. And here it is. And here is the formula and the name now that we can give this particular compound. Because not only did we discover it and identify it, but we thought I'd better give it a name. And a nice classical one is good. So it's called thicotrichite, and most geological specimens, minerals end in ITE, so that's good. And then, as you see, it's a hairy mineral growing from a storage cabinet environment. And of course, this is in a museum collection, so it's an important object. The surface has been consumed by the reaction, so the carving of this Egyptian cuneiform, this Egyptian stela is being eaten up day by day as this process goes on. And if we're talking slow but sure, this is not so slow. That museum object was in that destructive environment, made in this case of cabinets with artificially fiberboard type wooden drawers and wooden shelves. And it took about 1 year for those crystals to go. So a destruction of the surface, or the significant destroying of the surface in such a short time. But despite the fact that it was not known what this was in the 70s, then the slow but sure and patient science and the waiting for the right technique to appear to be able to undertake that allowed its identification some 30 years later. And the story has a nice ending, because here is Professor Van Tassel in his later years admiring the paper that explained all that and seeing the illustrations of the specimens that he supplied from the museum in Brussels, and which I brought back in my hand luggage on the plane without destroying the crystal structures. And so it was QED and a happy man. The late Professor Van Tassel, I have to say, alas. We can move on to slow but sure processes in stone conservation. And now, here it is, the equation, but don't worry about it too much. This is a story of a particular material. Its chemical name is called zinc hydroxychloride. Zinc we recognize, chloride we recognize. Chloride is cropping up a lot today, and the hydroxy is just a water-derived component. Its mineral name is given in the right-hand side of the equation and its formula. And it was first described, as you can see, in an article, French article. And that was rather a long time ago, 1855. And as you see also from the title, this is a man-made material that is made by these three components, two compounds of zinc and water. Mix them together, it hardens, and it gives ciment très solide, a very solid cement, and it's as hard as nails, I can tell you. And that was very useful in the 1850s, especially for dentists, because it was used as an early dental fill material. Fast forward, but to a different era, certainly, to 1915, and we come to its relevance here. This is the Royal Palace in the Dam Square in Amsterdam. And here in the tympanum, we have, since its inception, larger-than-life figures depicting all sorts of historical and allegorical scenes. We see it after a recent restoration, where the gold is shining from tusks of various animals and from swords, and the marble looks very pristine, except it doesn't really look like marble because it's been given a coating to make it look fresh. We can discuss whether this was a good conservation approach or not, but it looks good. The next slide shows what it had looked like before the conservation, where the marble had been eaten away steadily by atmospheric pollution, there was blackening, and the Carrara marble was gradually dissolving away. So much so that since its inception, it had had several campaigns of restoration. Whole heads of figures were recarved in stone, actually sandstone, to replace the marble, which again is an interesting conservation decision. Fingers, arms, noses. Until in the 1915 restoration, they decided to use, yes, you've guessed it, zinc hydroxychloride. And here it is. This head, for example, has had its nose and its chin replaced. And as you can see, the head is in a rather bad state of disintegration or erosion by pollution. That is the marble. The very solid cement, a century later, is looking rather good, as it does here, where the whole face was essentially cast in this material and applied to the deteriorated figure. So here we have a slow but sure assessment of the efficacy of this cement material. 100 years, more than 100 years, and now looking essentially as good as ever. That seems a good testimonial, so we must assume that it is being applied for such purposes, because of its good durability, very regularly. Virtually no work with this material has been done since the Second World War. It fell out of favor, it was abandoned, but justifiably. That's the question. And this is where this kind of examination and investigation, where we remade this recipe with all sorts of variables, mixing the quantities up slightly with slight variations to see what the results would be. And just without going into the full details, these are the kind of features that change as you make different versions of these three components added together to give cements, but they're not all of the same quality, and maybe they're not all of the same durability. And that's where now the slow but sure work could be done, but has not been done, to justify that this abandonment of this material is indeed unjustified, which is my hypothesis. And I think it's based on a misconception, because in some cases it could be, and there is a notion that it might be, that the chloride in the formula, which is known to be antagonistic to stone durability, could be causing the further erosion or encouraging the further erosion of the adjacent marble. But the research has not been done to either prove or disprove that that would be a problem. It's a project waiting for some more slow but sure research. If one dwells for a moment to try and see what man has done to predict slowly but surely the lifetime of products, then one can move to examine what might be a very valuable piece of research to see how waterproofing materials, current commercial materials, can protect stone, sculpture, facades of buildings, and so on from deterioration, or hydrofugation of by application of these materials. And here we have the experiment. We have it at the end of its 40-year lifetime. So again, a rather painstaking and thorough piece of research, where the Belgians, this is in south of Belgium, in that research station, took, as you see, various slabs of 40 different types of stone, kept a central band as the natural stone, and applied 2 bands to each stone of materials that were going to preserve it. This slide shows one aspect of what we found 40 years later, and they examined the progress of the efficacy of these products, and they actually tested 3 products sporadically used with enough spread to be able to understand which was the best out of the 3, and 1 was good and 2 were bad. And the aspect of the problem that we see here is that, of course, the central untreated part of each panel has darkened in most cases, but in many cases the right and left hand side has remained. What we don't see from this is that they also tested how the effectiveness of the repelling the water was, and they could do that by a simple experiment with a application of water, and they found that indeed there was 2 of the products were losing their ability to protect the stone in that way over this 40-year period. How would one find that out without doing such an experiment? And this is at the underlying part of all these slow but sure conservation experiments. As soon as you want to not make it so slow, you want to accelerate it in some laboratory experiment, then you make it less sure. Because there's only the real test of time in the actual circumstances that can give confidence that nothing has been introduced in an acceleration of the process that might distort the results. So indeed, slow but sure is a necessity for conservation and for other aspects of historical research involving science on art. For example, the analysis of glass objects. We're now moving from conservation to analysis. So we're in a sense moving from what I said earlier in the heritage science field to technical art history or archaeometry, and it could be called either. And the case in question here is relevant to another man of my connection, because he happened to be a neighbor. In my early career, he was living next door to me, which was pure coincidence and pure good luck, because it turns out that he was the first conservation scientist ever employed by the Courtauld Institute of Art in London in the 1930s, while one of the great conservation centres of the world. And for most of his career, after he left the Courtauld Institute, just before the 1940s, he was involved with completely different research. So he was very interested by me as a neighbour who had just been appointed as the first conservation scientist of Glasgow museums. And he found that it was very appealing that there I was all these years later, some 40 years later, in the same position as he had been in the 1930s. And when he was in that position in the 1930s, he had produced this paper on the left. And as you see, it's from a journal, actually a journal that is now defunct, but it was the progenitor of the most important conservation journal, Studies in Conservation. And there in the 1930s, he published with his co-worker, Marie Farnsworth, this work on Egyptian glasses. And this is not conservation, this is to understand the glass material and how the constituents give rise to the appearance of the glass that we see, for example, the color. And it was cobalt blue colors that he was particularly interested in, with the techniques that he was able to apply in the 1930s. In other words, very much more primitive than nowadays. The interesting thing about my encounter with him as a neighbor was that after our first meeting, where he enjoyed the chat and I enjoyed it even more, he disappeared for a moment and said, I'll be back. And he was back in 5 minutes with a shirt box full of dozens of samples of Egyptian glass that he had under his bed for the previous 40 years. You are now the one that I wish to donate this collection to, he said to me. And of course, that was a privilege, but also a responsibility to do something with them. And so it was that in conjunction with colleagues at the Corning Museum of Glass in upstate New York, probably the best museum of glass in the world, Dr. Robert Brill there, and instigated some analysis of samples like these, where in 2007, so we have now moved from 1935 to 2007, we reanalyzed these glasses to see what the new techniques could find. Basically, we found what the old simple techniques found, not a lot more. A little more detail, but we actually backed up his results where he was able to find out these following features. And I'll just let your eye run over them, as the most important thing is that it was the essentials of the way in which the cobalt was coloring the material, the importance to do with the source of the materials that were added to the glass. They were beginning to become signs of that from his early studies, greater signs, and we produced graphs of the different elements and how they related to each other. But essentially, these 4 simple conclusions said that in 2007, we know that the results of 1935 were pretty much what we now see. And it has a further slow but sure aspect in that things are moving so fast in science that the technique that we use there is a technique called atomic absorption spectrometry. Not really one of the mainstream techniques nowadays, because it's been replaced by superior and much more detailed instrumental techniques, which can tell you even more precisely, down to parts per, not just million, but even parts per billion of the composition of materials. And so it is that we're in the process of initiating a reanalysis with colleagues in Ljubljana who have laser ablation inductively coupled plasma mass spectrometry. I'm not saying that again because I don't know if I can, but it will tell us even more about these objects. And it's more as a tribute to Ritchie and his pioneering work, and also to demonstrate indeed the fact that we are able to tell more and more, but the essential details were never in doubt since the 30s. We find glass not in such good state as these objects, and a very brief, slow but sure aspect of glass in archaeological sites. Sometimes, like this Dutch glass on the top left here, there is corrosion that has been occurring within the soil. Bottom right shows what that looks like under magnification, where you see these whorls, and exactly through a tiny pinpoint, moisture gets into the interior of the glass, The surface of the glass remains almost pristine, smooth and undamaged, but inside the glass, there is corrosion occurring, giving these brown patches. That's part of the whole field of the deterioration of glass. Archaeological glass, museum glass, it's all under study. And it's all very important to understand how the composition of these glasses relates to their behavior over the long term. The slow but sure deterioration of the buried glass in this case. And that's obviously of relevance to things like nuclear waste encapsulation, where glassy materials can be involved. And one wants to make sure that they are not deteriorating with long-term problems. So it was, but a long-term experiment was set up. And very briefly, here are the two aspects of it. It's called the Balladon burial experiment. Balladon is the location in England where it was carried out. A site was found where glasses of particular compositions, historical glasses from different periods, Roman, medieval, so on, were buried. Samples were buried. They were well analyzed and they were well recorded. And several samples of each glass were buried in this site, with a prediction that on a logarithmic scale, they would be examined, stretching over basically 100 years to see how these samples were behaving. Here we have the site originally, and then some years later, not so very many years later, where trees had grown up and where vegetation had gone wild, and where they realized that they couldn't even find some of the samples that they'd put in. They managed to get 2 sets of examinations carried out, but then they also realized it's very difficult to compare the results of the further sets with the previous sets because, well, first of all, we want to use the modern material, modern methods, and they're much more sophisticated, but how do you relate that to what you saw with a simple microscope or the like? So things were changing. And of course, the other thing about a long-term experiment is you have to have a long-term person involved. I mean, if you're setting up an experiment that's intended to go 100 years, you're not going to have one researcher involved. You're going to have a series of them, and they have to pass information on. So continuity is always in question. In such environments, and we come now to the final example, we see 2 classes that do this kind of thing. And this is interesting because I'm very glad that Amy Walker is with us from this university, a material scientist, and she will recognize that this is showing a particular problem because this lead glass has turned black on the surface, and the blackened surface is also deteriorating and spalling off. That's one aspect of the next problem, which is basically concerned with blackened Delftware, the Dutch, tin glazed earthenware, which is so well known, blue and white designs, especially well known, but of course, many colored designs as well on plates and bowls and any Dutchware of that period, the late Middle Ages onwards. And what's been known is that slowly but surely, those pieces that end up in the appropriate adverse environments, such as cesspits, such as the bottom of canals, in other words, places where microbiological activity can take place in these rather nasty environments, slowly but surely, resulting in the designs of the glazes being completely obliterated. This is a cesspit. This is someone excavating, and this is the kind of things that are found. These glazes are almost as if they were made to be black, completely covered with a black glaze. Whereas originally it was a blue and white, it was a white background with blue design or multicolored design, now obliterated. And although these are fragments, of course, in such environments, valuable pieces are found, which are now of little purpose because one does not know the design, and they're certainly of no practical use as a museum display piece. But depots in the Netherlands and elsewhere, because this is not just a Dutch problem, have these pieces in store as archaeological material retrieved of interest, but waiting to be studied. Well, fortunately, in this university, and with the assistance and encouragement and enthusiasm of Ioda and Michael Thomas, this is now happening. Under Amy Walker's investigation, we are well on our way to begin to really understand what's happening on the surface in detail, because it's known that what caused the blackening on the left-hand side of this, but has now been cleaned to the right-hand side, is that the glaze which contain lead, as a lead glaze, typical type of shiny glaze, converted through the microbiological activity to a black compound, particles of which then form slowly but surely by the microbiological activity and obliterate the glaze. Here we see the good aspect of the conservation research that underpins this PhD project in this university, because it is possible to reverse that process. And this is a slow but sure process that is proving most effective, because it's quite possible to turn the blackened part into its original glaze appearance by the action of strong sunlight. Nothing more than hot sun, and that is the result. This example was covered on its right-hand half, exposed on the roof of the engineering department in Engineering Institute in Lisbon, where a strong summer sun brought about this restitution of the original appearance. Chemical processes do it too, but not as effectively. And it all involves chemically lead sulfide, the black problem, going to lead sulfate by an oxidative process within the glaze. Here it's happening now. These samples that you see here are on that very roof, waiting for the sun to carry out the bleaching process. Left-hand half obscured on the left one, right hand and the bottom half. And as we see, the right-hand example is a Chinese porcelain example, which is also showing this problem, but that's another story. How is it doing? It's been there since March. Left-hand one is appearing in the next slide. It's coming along. Not there yet, but what's revealed in this case is a kind of ochre colored design. The black is going and a completely obliterated design is appearing. Give it a few more months and slowly but surely it will be revealing all. Well, that's exactly the kind of scientific conversion process that University of Texas at Dallas, in the hands of Amy Walker, is able to undertake sophisticated research to see what the process entails. We know more or less what's going on, but we need to examine it in more detail. It may not be a straightforward conversion of one compound to another. There will certainly be more than enough results for a good PhD to come out of this and slowly elucidate the way in which not only does the blackening form, but the way it converts and any variations in the way it converts with sunlight or chemical treatments. This is what it looks like if you really examine parts of the glaze, these particles of the lead sulfide, and this is where it's been chemically changed to a white compound, the lead sulfate. And it's by something that anyone who is wanting to dye their hair will have in the bathroom cupboard, hydrogen peroxide. Nothing more, nothing less. And by immersing the object in that, that conversion occurs. But who's thinking it goes from a black compound to a white compound. The black compound completely obliterated the glaze. The white compound should completely obliterate it with a white. That aspect of the project is also now under investigation. And we know that it depends on how the light interacts with particles in a glaze. And there's reflection going on at the surface, there's absorption of the sun's rays, there's scattering of the material from the particles itself. And of course, with the help of our friend from the beginning of the lecture, who had worked out the wave theory of light, we now have at our disposal equations and theories and technologies and computer programs that can allow us to simulate this process. And here we see a computer simulation which has taken the refractive index of the particle, black, very high refractive index, the refractive index of the glaze. This is just an optical property of materials. They're very different. So the black shows up. And this is using the me theory and other theories based on that early work to understand what the particle size looks like at a certain percentage. And if it converts to white, now we have not a photograph of the object, but a photograph of the object with the superposition of the white particles, worked out by the me theory to be completely transparent. So the theory of light and why particles look the way they do now matches the observation of why it doesn't go from black to white, but it goes from black to transparent. And we can even work out what different particle sizes and what different particle concentrations would do and produce equivalent simulations with a variation of these properties. As for example, this one with a different concentration of a different particle size of the black rays, and this one with the trying to get the same opacity with white material, lead sulfate. But we now know that, of course, the particle size of the lead sulfide does not influence it, whereas the particle size of the lead sulfate does. So theory and observation are being joined together. All these things are an evolution of patience, of perseverance, of slow but sure research. I hope you felt that this has not been too slow and too long for you. It was my pleasure to talk to you, and thank you very much.
Great. Well, I want to thank Norman for this wonderful lecture. And I also want to thank our Zoom audience, and thank you for tuning in. And we hope to have more of these as we go forward.
Thank you all.